Okay, this is Dr. Olufemi Olunlade on Geodesy class. Fine day to you. We're on gravity and potential consideration. This afternoon we are going to be treating some things about gravity, about gravitation. We are going to be talking about gravity potential and also gravitational potential. We are going to be talking about normal gravity, also normal gravity potential. From there we go into disturbing potential, then gravity anomaly, from this one we go into gravity disturbance. It's different from disturbing potential. So from there, let's see whether we'll be able to get to deflection of vertical and also the components of deflection of vertical. So you are welcome to this studies. Let's go quickly into our studies. Already you know about gravity. Gravity, usually denoted as G, is a vector, and is the vector sum of gravitational potential, or rather gravitation, and the centrifugal acceleration due to the rotation of the earth. So the gravity, remember that I told you, is dynamic and it's a vector, and it's a vector sum of gravitation and centrifugal acceleration due to the rotation of the earth at the point of observation. Now, gravity potential, in its own terms, gravity potential is the potential due to G, due to gravity. And that gravity is, of course, is acceleration. It's also meter per second squared. So this gravity potential is the potential due to gravity. And when you look at gravity potential, this is a scalar. It's not a vector. And it's always denoted as, in real time, it's denoted as W. Gravity potential is denoted as W. So when you look at something like this on this diagram, you see this W, we are talking about gravity potential. Now, gravity potential is W equals to V plus. When you look at this addition here, this vector addition, the addition of the potential derives its formation from this also. So you can see that the gravity potential is the gravitational potential of the earth plus the potential due to the centrifugal acceleration. That centrifugal acceleration was as a result of the rotation of the earth at that particular point of observation. I hope you get it. So this and this, remember, they are not vectors, they are scalar quantities. So don't mix them up. Now, if we happen to find the grad of W, we can say it's the same thing as grad of V plus grad of phi. That grad is the gradient. Go back to your further mathematics. That grad of W will give you G. Will give you G, which is gravity acceleration vector. That grad V, gradient of V, will give you gravitation, or rather gravitational acceleration. That grad of phi, gradient of phi, will give you the instantaneous centrifugal acceleration, which is also a vector. Now, so that grad is going to give you vector, vector, vector. But until you find a gradient of this potential, you will not be able to get back at G. I hope that is clear. Now let us go to gravitation and gravitational potential. Gravitation and gravitational potential also is not now gravitation, remember we have started looking at that now, is the attractive acceleration due to mass of the attracting bodies. So if we have two bodies of M1 and M2, the two will likely be attracting each other over a distance r. Newton came up with his law, which says M1 M2 over r all squared is equal to the force. The force of attraction. This is gravitational force. It give you a G multiplied by M1, M2 divided by r squared, where M1 is the mass of 1, M2 is the mass of 2, and G is the gravitational constant. That is a constant. A constant. And this F is also a vector with magnitude this, and direction will be in the direction of a line joining the two bodies. So if the two bodies were M1 and M2, the force will be along this direction. But if it were M1 and M3, it will be G M1 M3 over R with R, big R. So it will be G M1 M3 over R squared, and the direction of the force will be there, not here. So the direction is very, very important also. That is gravitation. That gravitation, that force, will also be in SI unit. It's a force. Now, gravitational potential is the potential. Gravitational potential is the potential due to gravitation acceleration. So that potential that exists because of this gravitational acceleration between these two bodies is the gravitational potential of that particular. And the gravitational potential field is the space that is created gravitational potential exists. You see, the gravitational potential for these two bodies is different from the gravitational potential between these two bodies, because the field in which they operate is different from each other. So that field is gravitational potential field. The Earth as a spheroid is very, very important in the next consideration. The Earth as a spheroid. Now, it is a spheroid that is formed. Remember our clip 1 on physical geodesy class. The spheroid that is formed by rotating an ellipse around its minor axis. If this is the minor axis of an ellipse, when you rotate that ellipse along that minor axis round one revolution, it gives you an ellipsoid or a spheroid. That spheroid is called the ellipsoid of the Earth. When the ellipse that was rotated has its axis, the minor axis, as the north-south axis of the Earth. Note it is very important. When that axis, the north-south axis of the Earth, is the one that is rotated, that it has its ellipse rotated around it to form an ellipsoid. That ellipsoid becomes the ellipsoid of the Earth. And you will recollect that since the Earth, who has the north-south axis, that Earth is an irregular structure. There are hills, there are valleys, there are rocks, uneven masses around the whole Earth. So rotating an ellipse to form an ellipsoid, even though it may fit the Earth a little bit, but definitely that ellipsoid will not be a mathematical figure. It will not be a convenient mathematical figure. That ellipsoid generated in order to fit the Earth the way it is will not be a mathematical figure. So the one that will be a mathematical figure is the one that is of interest to the geodesist. And remember that once it is not a mathematical figure, the gravity potential on that surface, the gravity potential will not be constant. And once the gravity potential is not constant, then you will not be able to do some calculations that we would love to do. So it makes the geodesist to define what we call a normal ellipsoid. To define what we call a normal ellipsoid. And that normal ellipsoid is a reference ellipsoid. Note it, a reference ellipsoid. That is representing the Earth. Now, that ellipsoid, that normal ellipsoid is Earth-centered. The center of the Earth is the center of that ellipsoid. So we can call it Earth-centered. And is best fitting. So we are not talking about a theoretical ellipsoid that will best fit the Earth. So that concept gives us a consideration of an ellipsoid that we could say, okay, fine, this is an ellipsoid that is generating a gravity field. So that ellipsoid, normal ellipsoid, will be generating a gravity field with a surface that has constant normal gravity potential. Normal gravity potential. So that ellipsoid will be better than the ellipsoid that will be generated here. The ellipsoid generated here with the half ellipsoid will only be close to the geoid, and the geoid, you know quite well, is not a mathematical figure. So we are talking about a mathematical figure that is good enough and that can have a potential that is constant on its own surface. So the potential along the surface of the normal ellipsoid is constant. I hope that is clear.
Yes, sir.
Now, let us go to normal gravity and normal gravity potential. Normal gravity. Remember, we are now in the normal ellipsoid area. Now, normal gravity, when you talk about normal gravity, that's the gravity associated with this normal ellipsoid. Any gravity of consideration that we consider, we calculate, or we get due to our calculations on the normal ellipsoid, that gravity is called normal gravity. And in geodesy, we represent it by gamma. We represent it by gamma. So the normal gravity field, if there is normal gravity, then there will be normal gravity field. So the normal gravity field is the normal gravity field is the external gravity remember, normal gravity field is the external gravity field of a normal ellipsoid. So normal gravity field is the external gravity field of this normal ellipsoid. It is very, very important in our study, and I want you to hold it in your hand. Then the normal gravity potential will now be the potential due to that particular field. Let us go to what we call disturbing potential. Disturbing potential. Now, the difference between the Earth's gravity potential, remember we had a drawing here, and we had another drawing here. This one is the normal ellipsoid, and this is the half ellipsoid. Now, the gravity potential of any point on the Earth, if it is possible for us to be able to get it, and the gravity potential on the normal ellipsoid, if it is possible to have it, if we are able to have these two, of course, there will be a small difference. That difference is called disturbing potential. That disturbing potential is represented by T, and is same thing as W minus U. The gravity potential on the Earth due to the Earth ellipsoid subtracted from the gravity potential on the normal ellipsoid. Now, so in actual fact, we can say that this is the actual gravity potential, W, and this is the normal gravity potential. So the disturbing potential is the difference between the two. And remember, these are potentials, they are not vectors, they are scalars. And in order for you to get the vector equivalent, remember what do you have to do? To find the grad of each of them, and that is the gradient in mathematics. So when you find the grad of t, it becomes the grad of w minus grad of u. So gradient of t will give you what? Will give you delta g, which is a very important point in our discussion of gravity. Gradient of w will give you what? Will give you gravity acceleration, the g, which is a vector. Gradient, remember we are talking about on the surface of the earth here, on the earth ellipsoid. So gradient of u, we are now on the normal ellipsoid. Gradient of u will give you what? The normal gravity, that which is also a vector, normal gravity vector. Because we are talking, when you are talking of gradient of u, which is the normal ellipsoid, we are talking of the normal ellipsoid, and I told you that the gravity vector on it is denoted as normal gravity gamma. So this difference in the grad, the difference in the gravity acceleration vector between this and the normal gravity vector is called gravity disturbance. It's called gravity disturbance. So delta G is very important. But now let us now go into a brand new definition of instead of this delta G, geodesists now decide to define a value, and this value in red is called gravity anomaly. It is this gravity anomaly that we use instead of delta G. This gravity anomaly is not exactly the same as gravity disturbance, but they are slightly different. In some cases, we use this to replace this. We use gravity anomaly to replace delta G, which is gravity disturbance. We'll tell you the reason in the next slide, but here I can always tell you that they are not the same. Delta G, which is gravity anomaly, is the same thing as gravity disturbance minus a value. This value has its own I think is the 2 gamma. This is 2 gamma divided by G multiplied by N, where N is the geodal undulation. So it's not exactly the same as this, but in most cases geodesists prefer gravity anomaly to gravity, they are not the same thing. So let's now look into what closely into what we call, yeah, we soon end this slide. Look at what we call gravity anomaly properly. I told you gravity anomaly is theta G, and the gravity disturbance is delta G. This gravity disturbance is a vector. It has its magnitude and its direction. You can check literature for the magnitude, but the direction points towards either the excess mass or the away from the mass deficit. So this gravity anomaly is a special kind of difference. Let me define it now before we end this particular slide. Delta G remember we said delta G is the difference between the grad W and grad U. But delta G is also the difference between the gravity at a point P and the normal gravity at the corresponding point Q. You will understand it better here in this diagram as we are closing. Look at it very well. The gravity at a point P and the normal gravity at a corresponding point Q. Most essentially, when you have the ellipsoid and the geoid, when you have both of them, you have a difference, which is the geoidal undulation. Any observation on point P will give you a corresponding point on the geoid, which we denote as P0, and that will give you another corresponding point on the ellipsoid. But the corresponding point on the geoid ought to be at right angle to the geoid. But by the time you go down, it may not be at the right angle. You may not strike the geoid, the ellipsoid at right angle. But for it to strike the ellipsoid at right angle, that is where this gravity anomaly comes in. So the point P, gravity at this point P, when it's related to the geoid at P0, and the gravity at